Welcome to the video lecture on partial fraction decomposition. This video lecture is going to be about a new strategy that you can use to integrate integrals that have rational expressions in them, which are polynomials divided by polynomials, which is this example right here. Now, up until this point, until we learn this technique, the way we would solve this particular integral would probably have to rely on trig substitutions, but it doesn't quite have the right form of a trig substitution because normally we like to see a variable squared plus or minus a constant squared, and this has this middle term that kind of gets in the way of that. So before we can use a trig substitution, we're going to have to complete the square to turn this into a nicely factored form that more fits or better fits our criteria for trig substitutions. So take a look at that denominator, x squared minus 5x plus 6. If we want to complete the square on it, we're going to take a look at just those first two terms, x squared minus 5x. And in parentheses, when I factor those, I would need to have in parentheses an x minus 5/2 quantity squared, so that when I FOIL this out, I would get back the x squared. A minus 5/2 x plus another minus 5/2 x gives you the minus 5x. But I would also have in here a plus 25/4. So what we're going to do, I'm going to make a little bit of space here. I'm going to push that plus 6 off to the side, and I'm going to add in that 25/4 that shows up when we FOIL this out. But to balance this out, I'm going to subtract 25/4 as well. So I'm really just adding 0. Now these three terms here become this quantity squared, and negative 25/4 plus 6 is the same as negative 25/4 plus 24/4, or minus 1/4. So this integral becomes the integral of dx over x minus 5/2 quantity squared minus a fourth. So now it's in a factored form, but it's still got this whole quantity squared going on. We really don't like having this x minus 5/2 in there. It's too complicated. So what we could do at this point is a basic u substitution to change that x minus 5/2 into just a simple single variable u. And luckily here, the derivative on both sides is 1. So this is going to tell me that du is just equal to dx. So I could rewrite this integral as du over u squared minus 1/4. So now it looks a little bit nicer, and it fits that pattern that we need for trig substitutions. We've got a difference going on here. The variable being squared is coming first, minus the constant being squared. So the appropriate trig substitution to use here should be with a secant. We want to use u equals a secant theta, where the a comes from the square root of this 1/4. So we're going to need to let our u be 1/2 secant theta. Now if we do that, that means du is going to equal 1/2. The derivative of secant is secant theta tangent theta d theta. So let's substitute in what we have. Du becomes 1/2 secant theta tan theta d theta. And our u in the bottom gets replaced with our 1/2 secant theta, and we want to square that and subtract 1/4. Now a little bit of scratch work over here. 1/2 secant theta quantity squared is 1/4 secant squared theta. And when I subtract that 1/4 from it, that means I have a 1/4 in common, so I can factor it out. And if I factor it out, that leaves me with secant squared theta minus 1, which is just a tan squared theta. So this denominator becomes, all of this becomes 1/4 tangent squared theta. And on top we have that 1/2 secant theta tangent theta d theta. So now to simplify this, 1/2 divided by 1/4 is the same as 1/2 times 4, which is just a 2. So let's pull that constant out front into a 2, and I can cancel one of these tangents on the top and the bottom. So I'll still have that secant theta d theta on top, but I'll only have one tangent theta left on the bottom. Now neither of these are squared, so this wouldn't be a good candidate for using any kind of Pythagorean identities because I would need secant squareds or tangent squareds. So since I don't have that, probably the strategy that I would use would be to convert these back into sines and cosines so that I can see what I'm dealing with. So let's go ahead and try that. Secant theta is 1 over cosine theta. And remember that 1 over tangent theta is cotangent theta, and cotangent theta is cosine theta over sine theta. So that shows me that these cosines can cancel out, and 1 over sine theta is cosecant theta d theta. So now at this point, you have to be on your toes. With trig substitutions, the difficulty is that there's a lot of trig identities, trig derivatives, and trig integrals that you need to know. So when I get to this point, you need to recognize that there is an antiderivative out there that we know for cosecant theta. It's not one of the more common ones, but it is out there. So in order to integrate this, you have to recall what that formula is. And the antiderivative of cosecant theta is just the ln of cosecant theta minus cotangent theta. And that 2 will stay out front. Okay, so here's what we have so far. It's all good except that this answer is in terms of theta and we need it to be in terms of x's. So what we're going to need to do at this point is take that answer, so 2 ln of cosecant theta minus cotangent theta plus c, and we're going to need to back substitute. Now we used two different variables. First we changed our x into a u and then our u into our theta. So we need to go backwards from our theta into u and then change that u back in terms of x. So back up one step first and go to your trig substitution and use that to tell you what this is going to turn into in terms of u. So if we have u equals 1/2 secant theta, we want to isolate that secant theta by solving for it. So I'm just going to multiply by 2 on both sides, and that'll tell me that secant theta is 2u. If you need to, you can think of that as 2u over 1 so that you can set up your nice little right triangle here. And remember that secant theta is hypotenuse over adjacent. So my hypotenuse will be the 2u and my adjacent side will be the 1. So Pythagorean theorem tells me that the hypotenuse squared minus the leg squared under a square root will be the other leg. So this will be 4u squared minus 1. So in my answer up here, I need to know cosecant theta and cotangent theta from this triangle. So cosecant theta is defined to be hypotenuse over opposite side. So 2u over square root of 4u squared minus 1. And cotangent theta is defined to be adjacent over opposite. So 1 over square root of 4u squared minus 1. So this becomes 2 ln of 2u over square root of 4u squared minus 1 minus 1 over square root of 4u squared minus 1 plus c. Now in terms of simplifying here, what you could notice is that these have the same denominator, so you can consolidate this into a single square root of 4u squared minus 1 in the bottom and a 2u minus 1 on top. Now at this point, we're ready to plug in back in terms of x. So we go back up to here, and we know that u is x minus 5/2. So I'm just going to replace both of these u's with x minus 5/2 wrapped in parentheses. So 2 times x minus 5/2 minus 1 over square root of 4 times x minus 5/2 squared minus 1 plus c. Now normally we would stop here, and this is a legitimate answer, but it is pretty messy. So for the purposes of what we're going to see later on in this lecture, I want to show you how you could simplify this and what it turns into. So at this point, what I would probably do is distribute across the top. I'm going to get a 2x, and 2 times 5/2, the 2's cancel out and you just get a minus 5 plus this minus 1, so this becomes a minus 6 on top. And then underneath that radical, I'm going to do the same thing. We're going to get, let me do a little bit of scratch work here. We're going to have 4 times x minus 5/2 squared minus 1. Let's see what that turns into. If you FOIL out the x minus 5/2 squared, it becomes x squared minus 5x plus 25/4 minus that 1. If I distribute my 4 across, I get 4x squared minus 20x. The 4's cancel here, so I get 25 minus 1, which is going to give me 4x squared minus 20x plus 24. All of those numbers are divisible by 4, so let's pull out a 4. That leaves me with x squared minus 5x plus 6. I'm going to pull out the square root of 4 and turn it into a 2, and then I'm going to notice that x squared minus 5x plus 6 factors into x minus 3 times x minus 2. So this whole denominator right here becomes 2 square root of x minus 3, x minus 2. Now notice that these two terms on the top are both divisible by this 2 in the bottom. So I can go ahead and cancel out a factor of 2, and that'll leave me with an x minus 3 on the top. And then I have these x minus 3's and x minus 2's on the bottom underneath that square root. Now the x minus 3 on the top and the bottom is really the same base. The x minus 3 on the top is raised to the first power, but the x minus 3 on the bottom is raised to a 1/2 power because it's under the radical. So you can consolidate those by subtracting their powers. 1 minus a half is a half, and that's positive, so that's going to go in the top just like this. And in the bottom we still have that x minus 2, which is also being raised to a 1/2 because of that square root. And if you prefer, you can just use that square root all around the whole thing, or you could write this as x minus 3 over x minus 2 to the 1/2, just like that. Now, properties of logs tell me that powers can be brought down front, which is going to cancel out this 2 in the front. So we'll just have ln of x minus 3 over x minus 2 plus c. And last but not least, the log of a quotient becomes the difference of the logs. So this becomes ln of the numerator, x minus 3, minus ln of the denominator. So this is our final answer in its most simplified form. You can see that that's much cleaner and nicer than leaving it like this, but it's a lot of work to get there. Okay? Now what I want to show you is that this same exact problem can be done in a different way altogether. So what I want you to observe is that 1 over x squared minus 5x plus 6 can be broken down into two fractions, 1 over x minus 3 minus 1 over x minus 2. And that's true because if you get a common denominator on that right-hand side, then the numerator over here would become x minus 2, and the numerator over here in parentheses would be x minus 3. And when I distribute my negative across, the x's cancel, and negative 2 plus 3 is 1. So that's exactly what this is on our left-hand side. So this statement right here is true. You can verify that with some algebra. Now, how does that help me? Well, if I want to integrate 1 over x squared minus 5x plus 6 dx, and I know that 1 over x squared minus 5x plus 6 is equal to these two fractions, why not integrate these two fractions instead? And I can break these up into two separate integrals. And each one fits the form of stuff prime over stuff, because the derivative of x minus 3 is 1, the derivative of x minus 2 is 1. So both of these are ln's. This becomes the ln of x minus 3 minus the ln of x minus 2. We did all of our integrals, so we tack on a plus c, and there's our answer. And notice that is exactly the same answer that we got up here, but we did it with a significantly less amount of work than doing that big, yucky trig substitution. So the trick to these is being able to take a rational expression like this 1 over x squared minus 5x plus 6 and being able to break it down into these partial fractions. These are called partial fractions. If you can do that, then integrating the fractions becomes very simple to do. So that's the hard part, is figuring out how to turn this rational expression into its partial fraction decomposition. So that's what we're going to talk about next. So in general, many functions can be integrated more easily using this method that we just talked about. And this method is called integration by means of partial fractions, or sometimes we just call it partial fractions. In order to integrate using this method, we need to be able to decompose rational expressions into their partial fractions. How do you do that? Step number 1. You want to first check your rational expression. You want to look at the degree of the numerator and compare it to the degree of the bottom. If the degree on top is the same or bigger than the degree on the bottom, then that is considered improper and you need to do long division to figure out how to simplify it first. If the degree on the top is smaller than the degree on the bottom, then you're ready to move on to part 2. So step 2 says once you've got your fraction reduced, you're going to completely factor your denominator. And we're going to factor it into linear factors of the form px plus q, possibly raised to powers, or quadratic factors like this, possibly raised to powers. Now for each of the factors that show up in your denominator, for the linear factors, you're going to create a fraction for each power that this power up here goes to. So whatever your biggest power is in that denominator, you're going to create a fraction with a constant on top over that linear factor raised to the first power, a constant over that linear factor to the second power, plus a constant over that linear factor to the third power, and so on up until you reach that highest power. Then you're going to do the same thing with all of your quadratic factors. You're going to have a fraction for each power that's possible up until this maximum power. But because these are quadratic factors, you're going to have linear factors on top. Now this all sounds very complicated and confusing, so let's try an example and see what I really mean by all of this stuff. Okay, so here's my first example. I've got a rational expression here, a polynomial over a polynomial. The very first thing you want to do as a quick check is look at your degrees. You've got a square over a cube, so the degree on top is smaller than the bottom, which is good news. That means this is reduced. If it wasn't, then we would have to do some long division first. So we're ready to move on and factor this denominator as completely as possible. So the first thing I notice is that all three terms are divisible by an x. So let's pull out a GCF of an x. That leaves me with an x squared plus a 2x plus a 1. And that trinomial factors some more into an x plus 1 times an x plus 1. Now when you have a factor like this that repeats, you want to make sure that you write it as a power. So this would be x plus 1 quantity squared. And the idea here is that we are going to take this original fraction and we're going to decompose it into its partial fractions. Now for each factor that you see here, you're going to need a fraction or possibly more than one fraction if there's a power. So for this x, it's the only x factor that I see because it's x to the first. So I only need one fraction with an x in the bottom. Now this is considered a linear factor because it's x to the first. So on top of that, you always use 1 degree less, and 1 degree less than a linear would be a constant. So I'm just going to call that constant a. Then I move to my second factor here, which is this x plus 1 quantity squared. Now this is really considered a linear factor even though it's being squared. You might think it's quadratic if you were to FOIL it out, but it's really considered a linear factor because what's inside of here is to the first power. It doesn't matter what that outside power happens to be. So if you have a linear factor like x plus 1, you're going to have a fraction with an x plus 1 in the bottom for every possible power until you get to this highest power right here. So in other words, I need an x plus 1 to the first in the bottom, and I need an x plus 1 to the second in the bottom as well. You need every fraction accounted for, every power accounted for. You may not use them all, but you need to assume that they're there and then show otherwise once you solve for these coefficients on top. Okay, so I have an x plus 1 quantity squared, so I need an x plus 1 to the first and an x plus 1 to the second. If this had been x plus 1 to the 7th, for example, then you would have had x plus 1 to the first, x plus 1 to the second, x plus 1 cubed, 4th, 5th, 6th, and 7th. You would have had all of those fractions in your decomposition. Now on top of these, again, what I said before is these are considered linear factors even if they're being raised to powers. So on top should be 1 degree less than a linear factor, and 1 degree less than a linear expression would be a constant. And I want it to be a different constant than this one, so let's just call it B and C. So this is what the initial partial fraction decomposition looks like. Now it's our job to figure out what the A, the B, and the C need to be to make this statement true. Okay? So what we're going to do is we're going to equate these two sides. And I'm going to do that by getting a common denominator on the right-hand side. So the common denominator would need the x, and it would need the x plus 1 squared. And that's exactly what this was over here when you factored it all down. Okay, that's where it came from. So these two denominators are now equal. What should the numerator be if I get a common denominator over here? Well, this first fraction has the x, but it's missing both of the x plus 1's. So this numerator would be this a times both of these x plus 1's. The middle fraction has one of the x plus 1's, but it's missing the other one and it's missing the x. So this would be bx times x plus 1. And the last fraction has both of the x plus 1's, but it's missing the x. So the two denominators we know are equal because this factored into our x plus 1 squared. So that means the two numerators must be equal. So we're going to set them equal to each other. Now there's more than one way to solve for A, B, and C. I'm going to show you a couple of different strategies in this lecture. The first strategy I'm going to show you for this example uses the fact that if you choose x values carefully, you can cut down on the amount of solving that you have to do. Look at these factors here. If I let x be -1, that's going to make this go to 0 and this go to 0. So both of these terms would completely disappear and only this one would be left. So that's a good strategy because it reduces the amount of variables that I'll have going on. So let's let x be -1. So if I plug it in, I got to plug it in on the left side and the right side. 5 times -1 squared is just 5, minus 20 is -15, plus 6 is -9. -1 in here makes this go to 0, -1 in here makes this whole term go to 0, and c times -1 will be minus c. So that tells me that c must be 9. Now if I look up here, the other factor that we had besides the x plus 1 was the x. And that's going to be 0 at 0. So let's let x equal to 0 this next time around. So on the left side, this goes to 0, this goes to 0, and I just get 6. And on the right side, 0 plus 1 is 1. 1 squared is 1, so I'll just get that a. This 0 right here goes to 0, so the whole term goes away, and this goes to 0, so this whole term goes away. So the b and the c disappear. So this tells me that a must be 6. Now all I need to do is find b. Unfortunately, the only two denominators I had were x and x plus 1, which had 0 and -1 as their solutions. So to get the last variable, we're going to have to pick another x, and this could be anything at all. Just pick something nice and easy. I'm just going to pick 1. So if I let x be 1, I get 5 plus 20 plus 6, which is 31. 1 plus 1 is 2, 2 squared is 4, so this would be 4a plus, if I let x be 1, I'm going to get 1 times 1 plus 1 is 2, so this will be 2b plus c times 1 is c. Now fortunately, we already know what a and c are, so we can plug those in. So 4 times 6 plus 2b plus 9, that's going to give me 24 plus 2b plus 9, which is 33. So when I subtract 33, I'm going to get a negative 2, and when I divide by 2, that tells me that b is going to be negative 1. So with a little bit of arithmetic here, sometimes a lot of arithmetic here, you can find out what these three coefficients need to be able to break this yucky fraction into three simpler fractions. So now that I know a, b, and c, I'm going to plug them in, and that's going to turn this into 6 over x. b was negative 1, so this is going to be plus a negative 1 over x plus 1, plus c was 9, so 9 over x plus 1 squared. And the idea here is, instead of integrating this yucky fraction, since this is equivalent to this, why not integrate these three instead, which should be easier to do. So that's what we're going to do. Okay? So most of the work comes in solving for that a, b, and c. And once you know what those are, then you get your fractions, which should be fairly simple to integrate. So this is now what I'm integrating instead. You don't have to do this if you don't want to, but I'm going to go ahead and break this up into three separate integrals, and while I'm at it, I'm going to pull out my constants. So this 6 I'm going to pull out, and I'll just have dx over x. I'm going to pull out my minus, and I'll have dx over x plus 1. And I'm going to pull out my 9, so I'll have dx over x plus 1 squared. Most of the time, these will be ln's. Okay, so what you want to be on the lookout for is stuff prime over stuff. And these two are both that, because the derivative of x is 1, the derivative of x plus 1 is 1. So this is just the ln of x right here, 6 times the ln of x, minus the ln of x plus 1. Now this is not an ln, because the derivative of x plus 1 quantity squared would be more complicated than just a 1. But that doesn't mean it's impossible. What you can notice is, if we rewrite this a little bit, let's take that x plus 1 squared and let's move it up to the denominator with a negative exponent. Then this becomes pattern recognition. Here's your outer function. Here's your inner function g. The derivative of x plus 1 is 1, which I have implied in my integral, so I have the right g prime. I don't need to counterbalance or anything. So we have all the right pieces. All I have to do now is integrate that outer function. And the integral of something to the negative 2, you add 1 to that power, so it becomes a negative 1 over negative 1. What's inside stays the same, and that 9 is going to still be out front. So rewriting here just a tad, this becomes 6 ln of absolute value of x minus ln of absolute value of x plus 1 minus 9 over x plus 1, and then I'm going to put my c on the end. And there's my answer. Let's try another one. So here's what we have, another polynomial over a polynomial. So when you have something like that, what you're going to contemplate using is this partial fraction decomposition, assuming that you can factor that denominator. You want to be able to get some nice linear or quadratic factors so that you can break this down. Now before I jump into that, quick check. Degree on top is a 3. The degree on the bottom would be an x to the 4th if I FOILed it out. So the degree on top is smaller, which is good. That means this is reduced. So we're ready to go ahead and try our factoring. Now this factor here has an x in common, so if I pull it out, I get x times x minus 1. Unfortunately, this one does not factor because it's a sum of squares, not a difference of squares. So I have to leave that as x squared plus 4. So that means that this rational expression is going to be broken down into the following partial fractions. Each of these factors in the bottom is only to the first power. So I'm only going to have 3 fractions, one for each factor, an x minus 1, and an x squared plus 4. If any of these had been raised to powers, then I would have had to add on to this the additional fractions raised to all those additional powers. Now this x is a linear factor, so I'm going to want a constant on top. X minus 1 is a linear factor, so I want a constant on top as well. But this factor is quadratic because of that x squared, so I want 1 degree less, which would be a linear expression. So how do we show that? Well, the linear expression would have an x term, but it could also potentially have a constant term as well. So we write that as cx plus d. And all 3 of these fractions added together should give me back this one. And now it's my job to find the a, the b, the c, and the d. Okay, so the way that I do that is by getting my common denominators. So the common denominator is obviously going to be all 3 of these multiplied together. So the a has the x, it's missing the other 2. The b has the x minus 1, it's missing the x and the x squared plus 4. And the cx plus d, wrap that in parentheses, it's missing the x and the x minus 1. So the 2 denominators of the left and the right side here are already the same, so the tops must be the same. So what we're going to do here is equate the 2 tops. This one's going to be a messy one because we've got 4 different variables to solve for. So the more you have, the more arithmetic it's going to take. So sometimes these can be quite tedious in terms of all the algebra that it takes to solve for your A, your B, your C, and your D. So if we take a look at this, if we try to use the same strategy that we did on the last example, what I could do is I could look at my denominators here or look at my factors here and find out what would make those factors go to 0. So what would make x go to 0? Well, just 0. So let's choose x to be 0 and see what that gives me. So if I let x be 0 on the left hand side, this goes to 0, this goes to 0, so I get negative 8. And if I let x be 0 here, I'm going to get that a. 0 minus 1 is negative 1. 0 plus 4 is 4. And since x is 0, this x goes to 0, making this whole term go to 0. And this x goes to 0, making all of this stuff go to 0 as well. So everything else cancels out. And this tells me that negative 8 equals negative 4a. So that tells me that a must be 2. Now my other denominator that was nice was x minus 1, and that's going to be 0 at 1. So let's plug in x equals to 1 this time. 2 times 1 is 2. 2 minus 4 will be negative 2. Negative 2 minus 8 is negative 10. If I plug in 1, 1 minus 1 will be 0. So this whole factor goes to 0, so this whole term goes to 0. Similarly for this one, 1 minus 1 will be 0, so all of this goes to 0. The only one that doesn't go to 0 is the one in the middle with the b. So we'll get b. We're letting x be 1, and 1 squared plus 4 will be 5. So we get negative 10 equals 5b, so negative 2 is b. Now the other fraction had x squared plus 4 in the bottom, and unfortunately that doesn't have any nice real solutions to it. So we don't have any other nice x's that we could plug in that would make this simplify nicely. So the rest of this is going to be a little bit tedious to do. What we're going to have to do is pick another x. Let's try negative 1 this time and see what that leads us to. So negative 1 cubed stays negative. So this will be minus 2 plus a 4, which is 2, and 2 minus 8 is going to be negative 6 on that left side. I'm going to get a times negative 1 minus 1 is negative 2. Negative 1 squared is 1 plus 4 is going to be 5. Plus b times negative 1 times 5. Plus c times negative 1 will be a minus c plus a d times negative 1 times negative 1 minus 1, which is negative 2. Now remember, we know what a and b are. So I'm going to replace this a with 2, and I'm going to replace this b with negative 2. So this becomes negative 6 equals negative 4 times 5 is negative 20. This becomes positive 10, and I'm going to leave that negative c plus d in parentheses, but out front I've got negative 1 times negative 2, which is a 2. So we get negative 6 equals negative 10 plus 2 times negative c plus d. When I add 10 to the other side, that gives me 4. When I divide by 2, that tells me that 2 is equal to negative c plus d. Now that isn't enough to tell me just c or just d, but we are going to use that later on and create a 2 by 2 system of equations. And what we need to do in order to have that 2 by 2 system is we need another equation, so we're going to need another x. So let's let x equal, say, 2 this time. Okay, so if we plug in 2 up here, 2 cubed is 8 times 2 is 16. 16 minus 8 is 8. 8 minus 8 is 0. So that left side will be 0. Remember that a was 2, and 2 minus 1 will be 1, and 2 squared is 4. 4 plus 4 will be 8. Remember that b was negative 2. This x becomes 2, and 2 squared plus 4 is 8. And then when we plug in 2 here, we're going to get 2c plus d times 2 times 2 minus 1 is 1. So this is 0 equals 16 minus 4 times 8 is 32, plus that 2 right here, which I'm going to put in front of my 2c plus d. So this is 0 equals negative 16 plus all this other stuff. If I add the 16 over to the other side and divide by 2, I get 8 equals 2c plus d. There's my second equation in my 2 by 2 system. So now what I want to do is use these two equations to solve for c and d. What I'm going to do is I'm going to multiply this top equation through by a negative 1, so it becomes minus 2 equals plus c minus d, and I'm going to leave this bottom equation the way it is. And if I add the two together using this elimination method, the d's cancel, and we get 3c equals to 6, so c must be 2. And then if I go back to here and plug in 2 for c, I get 2 equals negative 2 plus d, so that tells me that d must be 4. So we have a, which was 2, b, which was negative 2, c, which was 2, and d, which was 4. So those are going to go on top up here. So this is going to become 2 over x minus 2 over x minus 1. I just put the minus in front, plus 2x plus 4 over x squared plus 4. So instead of integrating all of this, I'm going to integrate these three instead. Okay, so all we've done so far is all the algebra it takes to get the a, the b, the c, and the d. That's the tedious stuff. The actual integrating will actually be pretty easy to do. So let's pull this down and go ahead and do that on the next page. So what we're integrating is 2 over x, that was our a, minus 2 over x minus 1, that was our b fraction, plus 2x plus 4 over x squared plus 4 dx. So there were the three fractions that we had. Now I like to break these up, so I'm going to take this first fraction, pull the 2 out, and just write this as 1 over x dx. And then I'm going to take this 2 out and write this as 1 over x minus 1 dx. Then for this third fraction, you have a sum in the numerator. Unfortunately, this is not stuff prime over stuff directly because you've got that extra plus 4 on top. But because you have that sum, you can break this up into two fractions, this one and this one. So that's what I'm going to do. I'm going to have 2x over x squared plus 4 plus 4 over x squared plus 4. So I'm breaking up that sum between the cx and the d. So let's see how this helps. This one here is just ln of x, right? The derivative of ln of x is 1 over x. So this is 2 ln of the absolute value of x minus 2. This is also an ln because the derivative of x minus 1 is 1. So you have stuff prime over stuff. So this is 2 ln of the absolute value of x minus 1. This is also an ln because the derivative of x squared plus 4 is just a 2x. So we don't even need to modify anything here. I'm just going to have the ln of that denominator. I have all the right pieces already. Now this last one is not an ln because the denominator would have as its derivative a 2x, and I don't have that x. That x is missing. So what I can do is take this 4. It's not helping me at all. Let's pull it out. And then think of this as 1 over x squared plus 4. Now that should look vaguely familiar to you. This is of the form 1 over x squared plus a squared dx. We do have a derivative or integral rule for that. It's an arctangent. This is actually 1 over a inverse tangent of x over a. So that's the rule that I'm going to use here. And you see these quite often with these partial fraction decomposition problems. So I'm going to have a 4 out front, but I'm going to get a 1 over a out front as well. And the a here would be 2, the square root of this 4. So I'm going to get a 1 over 2 arctangent of x over 2 plus a c. And if you want 4 times a half, that's just going to turn into a 2. So here's my final integral completed. Okay, on the next example here, we've got 8x cubed plus 13x over x squared plus 2 quantity squared. Checking the degrees really fast, we've got a cubic on top, and an x squared squared would be an x to the 4th. So this is reduced. The degree on top is smaller. So we're ready to go ahead and jump in. And if you look at the denominator, it actually already is as factored as it's going to get because x squared plus 2 does not factor any further. But it is a factor that's being squared. So be careful here. This is kind of tricky for students. They'll have a lot of problems remembering to do what we're going to do next. What you're going to do is realize that the only factor that I really have here is this x squared plus 2. It's just that it gets repeated. So in partial fraction decomposition, you have to have a fraction for every factor that you see plus every possible power of that factor. So this would be x squared plus 2 to the first, or I could also have x squared plus 2 to the second because my highest power here is 2. So I want every possible power leading up to that 2 accounted for. Okay, so you're actually going to get two separate fractions here. Now the other thing to notice is that this factor inside the parentheses is actually a quadratic factor. So 1 degree less than that would be linear. So on top we need to see a linear expression, which would be something of the form ax plus a b. You could possibly have a constant in there as well. This factor is also considered quadratic, even though it's being squared, because what's inside is quadratic. So it needs a linear expression on top. So let's call it cx plus d. Okay, so here's my partial fraction decomposition. What I want to do now is equate the two fractions. So we've got 8x cubed plus 13x over x squared plus 2 squared. If I get a common denominator down here, which would be the x squared plus 2 squared, these two denominators should be equal. Then on top, what I would have to keep these equivalent would be this ax plus b. It only has one of these x squared plus 2's, so it's missing the extra one. However, the cx plus d already has both, so I don't need to multiply that top by anything. So now that the bottoms are equal, the tops must be equal. Now what I'm going to do on this one is a little bit of a different technique, just to show you another option. This is a good technique to use on a problem like this because the denominator here doesn't ever equal to 0 at a nice real number. So there wouldn't really be any good x values that we could let our x be and plug in and hope that it would simplify nicely. So in a case like that, what I like to do instead is to go ahead and distribute out everything on this right-hand side. So what I'm going to do is I'm going to FOIL out over here. I'm going to get an ax cubed plus a 2ax plus a bx squared plus a 2b plus that cx plus d. And now what I'm going to do is I'm going to put this in decreasing order on that right-hand side. And I'm going to group together my like terms. So there's only one cubic term, so let's put that one first. There's only one square term, so that one goes next. But there's two x terms. So I'm going to factor out the x and in parentheses write the coefficients, which would be the 2a plus the c, and the x goes on the side. And then my constant terms, the ones without the x's, are this 2b plus d. So I'm going to put those in parentheses as well, and that's kind of like my x to the 0 term, my constant. So when we do it this way, after we do the work of FOILing this all out, what we're going to do here is we're going to equate coefficients of like terms on the left and on the right side. So on the left side, the cubic term has a coefficient of 8, and the only cubic term on the right side is this ax cubed. So the only way these can be equal is if a is equal to 8. So that tells me a. And that's just by looking at the cubic terms. Now if I look at the square terms, there is no square term over here. So the coefficient of the square term on the left is a 0. What's the coefficient of the square term on the right? It's this b. So that means b must be 0. Then over here, the linear term, the coefficient is a 13. And on the right side, my linear term has this coefficient 2a plus c. But remember, we know what a is. A is 8. So that tells me that 13 equals 16 plus c, so c must be -3. And now if I look at my constant term, there is no constant on the left, so that's a 0. And my constant term on the right is 2b plus d. We know that b is 0, so this term becomes 0, so that forces d to be 0 as well. So that means my fractions become 8x plus 0 over x squared plus 2 plus cx, or -3x, plus 0 over x squared plus 2 squared. So this is going to look like 8x over x squared plus 2 minus 3x over x squared plus 2 squared. So the b and the d were both 0, so we don't need those constant terms on top at all. And this partial fraction decomposition is the same as this right here, just in a different form. So instead of integrating the original problem, let's integrate these two instead. And hopefully that'll be easier. So I'm going to break these up into two separate fractions. I'm going to pull the 8 out. So this would be x over x squared plus 2 dx. And then I'm going to pull this 3 out and write this as x over x squared plus 2 squared dx. So now to integrate, be on the lookout for ln's. I always check for stuff prime over stuff. This one is almost that way. We have x squared plus 2 in the bottom, so the derivative of that wants to be a 2x. I have the x, I'm missing the 2, So I counterbalance out front. 8 over 2 gives me 4, and now this is stuff prime over stuff, which has as its integral an ln. So this is ln of that denominator. Then for the second one, we can't do that because the derivative of this bottom would be much more complicated than just an x. So this is not going to be an ln. But I can do a little bit of rewriting. Let's take that denominator and let's move it up to the top with a negative exponent. And now this is pattern recognition. This is your f prime. This is your g. The derivative of g wants to be a 2x. I have the x, thankfully, but I'm missing the 2. So put it in and counterbalance. So we get minus 3/2 out front. The only piece here that you integrate is that outer function. When you add 1 to a negative 2 power, it becomes a negative 1 power over negative 1, and what's inside stays put. So rewriting this is 4 ln of x squared plus 2. Minus minus becomes plus. I get a 3 on top and 2 times x squared plus 2 on the bottom once I move that down, plus a c. Okay? Now this next example should look completely different than all the other ones we've done so far. It doesn't look like a polynomial over a polynomial, but that doesn't mean we can't use the same strategy if we do a little bit of creative thinking here first. Now when I look at this, what I tend to see here is that I've got this relationship between sine and cosine. I know that the derivative of sine is a cosine, and I have this one little extra cosine kind of floating around, which might be ideal for using as part of that du. So let's try a little u substitution and see if that improves matters here at all. Let's let u be sine of x, and then du would be cosine x dx. So all of this becomes my du, and in the bottom we're just going to have a u right here and a u minus 1 right here, and there was nothing left in the top since that cosine joined up with the dx to give you that du, so we just have a 1 on top. Now if I gave you this problem, this is perfect for pattern recognition. It's already factored in the bottom, the degree on top is smaller, so we should be able to break this down into 2 fractions because there's 2 factors in the bottom. We would need a u and a u minus 1. Both of these are linear, so they're both going to have constants on top, so an a and a b. So the common denominator here for these two would be u times u minus 1. So the a is missing the u minus 1, the b is missing the u, and this is supposed to equal 1 over u times u minus 1. The bottoms are already equal, so the tops must be equal. Now this one has some nice zeros. If you want this factor to go to 0, you would need to let u be 1. So let's let u equal 1. The left side is 1. If u is 1, this goes to 0, so this whole term goes to 0, and I just get b times 1. So b must be 1. Now if I look at this term here, this will go to 0 when u is 0. So let's let u equal 0. The left side is still 1. 0 minus 1 is negative 1 times a, so negative a. And if this is 0, b times 0 will be 0, so this whole term disappears. So that tells me that a is negative 1. So this becomes negative 1 over u plus positive 1 over u minus 1. So let's integrate these instead. So if you need to, you can break this up into 2 separate integrals, negative integral of 1 over u du plus integral of 1 over u minus 1 du. Both of those are stuff prime over stuff, so both of those are ln's. So this is negative ln of u plus ln of u minus 1 plus a c. Unfortunately, we're not done yet though. This is in terms of u, we need x's, so go back to here. U is sine of x, so all I have to do is plug in sine of x for these u's, and then I am done. And there's our answer. So even though it didn't start out as a rational expression, we were able, with a use substitution, to turn it into one and then use this partial fraction decomposition method to be able to integrate fairly easily. Okay, on this next example here, I want you to do your quick check right away. Notice that the degree on the top is 3. The degree on the bottom is a square. So that means this is not considered to be a reduced fraction. So before we even jump into factoring and partial fractions, you must do some long division here first to reduce this before you go any further. And we have to use long division as opposed to synthetic division because what we're dividing by here is a quadratic function, not a linear function. Synthetic division only works when you're dividing by linear functions. So how do we do long division again? Well, we're dividing by this denominator. So we need x squared minus x minus 2 out front, and we need this numerator underneath our division bar. Notice that there's no x squared term here, so I want to hold its place by giving it a coefficient of 0 because I might need an x squared term when I do my long division. So it's good to have space for it. All the other terms are accounted for, and make sure these are in decreasing order. So now what I do is I say x squared times what would give me x cubed? Well, that would be x. X squared times x is x cubed. Negative x times x is negative x squared. Negative 2 times x is negative 2x. Make sure you distribute this x to all three of these terms and line that up underneath the corresponding like terms. Then we need to subtract. Remember that we're subtracting this entire bottom row, so you need to change your signs of all three terms. So this becomes minus, plus, and plus. These should cancel. 0 plus x squared is x squared. Negative x plus 2x is positive x, and then I bring down my 3. Now I can do this again. X squared times what gives me x squared? Plus 1. So x squared times 1 is x squared. Negative x times 1 is negative x. Negative 2 times 1 is negative 2. Draw your line. Change your signs. So minus, plus, plus. These cancel. X plus x is 2x. 3 plus 2 is 5. Now this degree is too low. It's a first degree and we need 2 or higher to be able to continue our long division. So this is it. We're done. But this is going to be part of our remainder. This is our quotient. So remember how you write out what this is. What we've just found out is that when you do this division right here, you get x plus 1, nice and big, that's your quotient, plus a remainder fraction, where this remainder down here is the numerator, and what's on the bottom should be the same divisor that you had originally. So the denominator stays the same. So instead of integrating this, we're going to integrate these three things. Now this should be easy, the first two here, because the integral of x is just x squared over 2, and the integral of 1 is just x. But this one, not so obvious. Okay, it's not stuff prime over stuff, because you would need a derivative of 2x minus 1, and we have 2x plus 5. So this is going to be a little more challenging, but it now has the degree on top being 1, and the degree on the bottom being 2. So this is now reduced. So you can potentially do partial fraction decomposition on this if that denominator factors, which it does. It becomes x minus 2 times x plus 1. So we're going to do a little partial fraction decomposition on just this last part over here, this remainder fraction. So let's take 2x plus 5 over x minus 2x plus 1, and let's decompose it into a fraction with an x minus 2 and a fraction with an x plus 1. Both of these are linear, so we need constants on top. Getting a common denominator, we would have a times the x plus 1 plus b times the x minus 2 for the numerators. And that numerator needs to equal the numerator over here on the left. So 2x plus 5 needs to equal a times x plus 1 plus b times x minus 2. What would make this factor go to 0? Negative 1. So let's let x be negative 1. So that would give me 2 times negative 1 plus 5, which is 3. This goes to 0, and negative 1 minus 2 is negative 3b. So that tells me that negative 1 equals to b. What would make this factor go to 0? 2. So let's let x be 2. 2 times 2 is 4. 4 plus 5 is 9. 2 plus 1 is 3, so this will be 3a, and this term goes to 0. So this tells me that 3 equals to a. So this fraction becomes 3 over x minus 2 plus negative 1 over x plus 1. So we want to integrate those two things instead of integrating this guy, instead of integrating up here. So we're going to integrate these instead. Now don't forget, it's easy to forget, but remember we had in front that x squared over 2 plus that x as well. That came from the pieces of our quotient that we got over here. So that's still in front. Don't lose those. So this is what we have so far. This x squared over 2 comes down plus our x. This one is 3 times dx over x minus 2, and this one is dx over x plus 1. Both of these are stuff prime over stuff. The derivatives are 1. So they're both going to become ln's. So we have x squared over 2 plus x plus 3 ln of x minus 2 minus ln of x plus 1 plus c. Okay, our last example here, the integral of du over u squared minus a squared. Now, on this particular integral, keep in mind that there are other options, okay? When you look at this, what you might first think of when you first see this is actually a trig substitution, because it's exactly in the form of the trig substitution patterns that we learned in a previous lecture. This has your variable squared minus your constant squared. So when you have that, when you have subtraction with the variable coming first, then this is ideal for a u substitution where you let that u be a times secant theta. Now, as you've probably learned by doing some trig substitution problems, these are pretty time consuming and tedious to do. So if you can avoid doing a trig substitution, that's great. The only way we're going to be able to avoid doing that is if this denominator factors, which it does, right? It's a difference of squares. So this denominator is u minus a times u plus a. So that means that this should break down into partial fractions, a u minus a for one of them and a u plus a for the other. And the u is the variable here, and these are u to the first. So these are linear, which means I need constants on top. So let's figure out our big A and our big B. On the numerator here is implied to be a 1. So this is 1 over u minus a, u plus a. So when I get my common denominator on the right hand side, it would be this big A times u plus a plus b times u minus a. So equating the two tops, what value of u would make this go to 0? Negative a. So let's let u equal negative a. This stays 1. Negative a plus a goes to 0, so this disappears. Negative a minus a is negative 2a times b. Little a here is a constant, so I can divide through and get negative 1 over 2a as my value for b. So that's the one that made this go to 0. What's going to make this go to 0? Well, that will be 0 if u equals a. So let's let u be positive a. So we get 1 equals a plus a is 2a times big A, and this goes to 0. So that means 1 over 2a will be capital A. So these fractions become 1 over 2a times u minus a plus negative 1 over 2a times u plus a. So to integrate this, we can integrate these instead. If I break them up, I'm going to take this and pull it out. Those are constants. So this would be 1 over 2a times 1 over u minus a du minus 1 over 2a 1 over u plus a du. So I broke it up and pulled these out front of their respective integrals. And then this is stuff prime over stuff prime over stuff, because the derivative of u is just 1. So both of these are ln's. So this is 1 over 2a ln of u minus a minus 1 over 2a ln of u plus a c. You can stop here if you want. I do want to show you an alternative answer here. Since these have the same coefficient, 1 over 2a, you can factor that out, and this would be ln of u minus a minus ln of u plus a. And sometimes what you'll see in textbooks when you look at your answer in the back of the book is they may have a slightly different version of the answer that looks different than yours. And most likely that's because they have used some properties of logs to consolidate their answer. So let me just show you how you could do that on this one. If you have a difference of two ln's, that becomes the quotient of their arguments. So the u minus a, the one that comes first, is on top. The one that comes second is on the bottom. And that 1 over 2a stays out front. So you could also see this answer written this way as well. So don't freak out if you look in the back of the book and your answer is different. You may be able to manipulate yours to look like theirs, but both answers are correct. Okay? Alright, that concludes our video lecture on partial fraction decomposition. Good luck.